Let's talk about ZooKeeper next. It's an important system for maintaining data across your entire cluster in a consistent manner. So what are some examples of things that ZooKeeper might have to do? Well, for example, if you're running on a distributed system, like let's take HBase as an example, every client has to have a consistent picture of who the master node is that it's writing through. If you have more than one master responding at a time, then you can get very inconsistent behavior in your database, and that's a bad thing, right? So if you're building a system where you care about consistency above all else, you need to have some sort of a system outside of your system that's keeping track of these things. So in addition to which node is my master server, what tasks are assigned to which workers? So if a worker fails, how do I know where to pick up from when I redistribute that work? What workers are currently available? That's something else that every client needs to know about potentially. So it's basically an external tool that applications like HBase can use to recover from partial failures in your cluster. And believe me, in the real world, these failures do happen. Individual nodes go down, networks do weird things. You can have like storms on your network that partition your network in strange ways. Hard drives fail, you name it. I mean, I've seen it all. Clocks will drift. Some systems might think they're in a different time zone. All of these things can wreak havoc with a distributed application. And ZooKeeper is an attempt to build a system that sits off to the side and tries to maintain a consistent picture of state on your entire distributed system in a consistent manner. So in addition to HBase, it's also an integral part of high availability MapReduce. Drill uses it for maintaining state across its servers, and some systems we haven't talked about yet, like Storm and Solar, but you might have heard of them, also use ZooKeeper extensively. So let's talk about some of the failure modes that ZooKeeper can help with. For example, let's say you have a single master system like HBase, or Yarn works this way as well too, right? It has to go to a resource application master to distribute work to worker nodes. So we've seen this pattern very frequently throughout this course. So what happens if that master goes down? Well, in a high availability system, you'll have other masters that are just running there as a backup. And all of these clients that are talking to this system need to agree on who to talk to as a master. So ZooKeeper can keep track of who the current master is, and if that master goes down, automatically detect that it's no longer responsive, and let these other masters try to make themselves the new master, but only allow one to actually win that race, so that it keeps track of who the master is. Also, if a worker crashes, ZooKeeper can detect that sort of a failure as well, and say, hey, we haven't heard from this worker in a while, something went wrong, or it explicitly disconnected for some reason. Then it can notify your application that that happened, and your application can then redistribute the work accordingly. Or let's say you have some sort of a network problem. Maybe these two workers are in one data center or a rack, and this is on a different data center or a different rack. And for some reason, those two data centers or those two racks can no longer talk to each other. Well, if ZooKeeper is off here, it will be able to detect that sort of a failure mode as well, and say, hey, I'm getting inconsistent reports about whether this worker can actually be reached or not. You better deal with that, Mr. Application. So we talk about primitive operations when we deal with these sorts of failure modes. There are certain basic tasks that a system like ZooKeeper has to take care of. One is the master election that we talked about, making sure that only one node at a time is the master, detecting crashes or other sorts of failures of communication. So we can deal with that by having ephemeral data on a node's availability that automatically goes away when that node disconnects or fails to provide a heartbeat over some certain time frame. We can also keep track of group management, keeping track of what workers are available in your pool. And we can also keep metadata associated with your entire cluster that needs to be consistent, such as a list of outstanding tasks and task assignments, so that if one of your workers goes down or your master goes down, the new nodes that come in to take its place know where to pick up from. Okay, that way you can make sure that you don't miss any information throughout that failure. But ZooKeeper takes a different approach. So if I were going to build a system to solve those problems, I would just build a system that had an API like, choose a master, who is the master, or tell me who's in this worker group. But ZooKeeper is much more general. So the idea here is that instead of providing these very specific APIs for specific problems, instead it provides this very consistent little distributed file system that any application on a distributed system can write to and read from. And by making this more general system, it kind of pushes the logic of how to deal with these failures to individual applications, but it does solve the problem of making sure that data is stored consistently and reliably to every node on the cluster. So, for example, you can think of ZooKeeper like this. Think of it as a file system that lives on a little tiny distributed cluster of its own. And we might have a root to our file system under the /root. and maybe there's a /master file that lives under that root that contains the data master1.foobar.com:2223. So this /master, actually a Z node is what you call it in ZooKeeper, not a file, but the concept is the same. This master Z node might contain this data that tells the rest of your cluster who the current master is. And if the person who wrote that, if master1.foobar.com went down, it might automatically release that node and let someone else take its place instead. But ZooKeeper would handle all the complexity of making sure that only one client at a time has ownership over that master Z node. You might also have a workers Z node under the root that might contain multiple Z nodes under it. So you can have these hierarchical relationships, these parent-child relationships, where it might keep a list of all the available workers that are currently available to the cluster. And again, if one of these workers were to go down, then thanks to the ephemeral state of these nodes, that would automatically go away, and other workers could actually get notified of that happening and respond accordingly. Speaking of notifications, that is an important feature. So clients can actually subscribe to notifications on a Z node. So if it goes away or if it changes, it can automatically be notified of that from ZooKeeper. So that avoids the need for continuously pulling this data from every client, which would obviously be very intense on the network as opposed to this other model of notifications. So for a concrete example, if a specific client registered itself as the master by writing to the master Z node, if the current master were to go down, thanks to the ephemeral nature of that Z node, that master node would then become empty, and all the other clients could get a notification that master changed and it now has nothing in it, and those clients could then try to become the new master, and ZooKeeper would ensure that only one actually succeeded. And that way we only have one master at a time, and everyone agrees on who it is. So we've talked about the usefulness of ephemeral Z nodes that automatically detect if the client crashes or loses its connection to ZooKeeper. It's very handy for things like master election. But you can also store persistent Z nodes. So even if the client that wrote that data goes away unexpectedly, that data can still persist unless that is explicitly deleted. So for example, the assignment of tasks to workers should persist even if the master node crashes. So if the master goes down, you still want that information of the outstanding work that needs to be done to live on, so that when the new master picks up, it knows where to pick up from where the previous master left off. So very important key to ZooKeeper, both persistent and ephemeral storage. Persistent is, well, what it sounds like. It's stored persistently even if the person who wrote it goes down, but ephemeral nodes will go away automatically if the client that created it either crashes or loses its connection. And that's how we can deal with failure modes of individual clients going down. Architecturally, ZooKeeper looks like this. So you might have your application over here on the side doing whatever it does. Maybe it's HBase, maybe it's MapReduce, maybe it's a Yarn client. But fundamentally, every client in your application will link into ZooKeeper client that allows it to talk to your ZooKeeper ensemble. So typically, you'll want to have more than one ZooKeeper server, or else it itself becomes a single point of failure. So, who's watching the watchers, right? It doesn't do much good to have ZooKeeper running on one server, because then if that ZooKeeper server goes down, your entire system is unavailable, and that would be terrible. So typically you want more than one server, and we call that a ZooKeeper ensemble. So the way it works is your clients, your ZooKeeper clients, need to maintain a list of what all these servers are that it can connect to, and it will choose them, in a distributed manner so that it tries to spread out the load as much as possible. And the ZooKeeper ensemble is responsible for replicating data in amongst itself. So when one of these workers says, I want to write something to a Z node, it will actually wait until some specified replication factor comes back. For example, you could say, I want a consistency level of 3 servers, and it won't respond back and say, okay, that's been written, until it's actually been confirmed to have replicated to at least 3 servers. And that way you can make sure that you have some guarantees of consistency. ZooKeeper quorum. So remember when we talked about MongoDB? This is going to sound pretty familiar. The idea is that you can specify the minimum number of servers that need to agree on something before you accept the answer as a client to ZooKeeper. So for that reason, you typically want not only just more than one ZooKeeper server, but more than 3. And in particular, if you want to be able to tolerate more than one ZooKeeper server going down, you need at least 5. And let's talk about why that is. So let's say, for example, you have an ensemble of 5 ZooKeeper servers, and you only set a quorum level of 2. So you say that you'll accept a result if at least 2 servers agree on it. Well, what happens if there's some event where we have a network partition of some sort? Let's say these 2 servers are in one data center and these 3 are in another, and all of a sudden this data server can't talk to this data server because of some network failure. Well, if I had a ZooKeeper quorum of 2 set, I could get into this inconsistent state, where if a client is talking to these 2 servers, they agree on what a given node contains, but they're not able to replicate that node to these other 3. So if another client comes along and talks to these 2 servers, they're going to get a different answer. But things will still keep on running because we only had a quorum of 2. So these are both valid answers from the standpoint of this setup. That's a bad thing. This is what we call a split brain scenario, where we can have part of ZooKeeper providing one answer to clients and another part of ZooKeeper providing a different answer to clients. And that sort of inconsistency is exactly what we're trying to avoid with ZooKeeper. So ZooKeeper is not a cure-all. You need to be very careful about how you set it up and how you configure it. Now, the solution here would be to have a quorum of 3 at least. So that way, as long as a majority of servers agree on a result, you're probably okay. So with a quorum of 3, I would, in this case, get an answer from these 2 guys and notice that the third one didn't agree with it. And then my application could say, something's wrong here, that failed, and deal with that failure accordingly. Or if it talked to these 3, it would get, the same answer, but it would at least be replicated with these 2. So it's important that you have at least 5 servers with a quorum of 3 to get reliable performance out of ZooKeeper. And ideally, you usually want to have these spread across different data centers too, right, for even more redundancy. So this sounds a lot like some of the things I was criticizing MongoDB for. And if I sounded critical about MongoDB when we were teaching MongoDB, that's not really fair, because ZooKeeper has the same exact problems as MongoDB when it comes to dealing with consistency and the availability of that system. I mean, we talked about the cap theorem, and that's just the trade-off here, right? So since we are both HBase and MongoDB value consistency above all else, the trade-off it's making is on availability. So we have this, sort of very complex and very fragile system. Well, I shouldn't say very fragile, but it has failure modes of its own that keeps track of the consistency between all of these different systems. So, MongoDB HBase is just sort of the nature of the beast when you're choosing consistency over availability. If you have something like Cassandra, however, that's totally different, right? That's choosing availability over consistency, and that's why Cassandra doesn't have these sorts of problems. You just have to look at what the requirements of your application are. If you're like me and you're writing applications that just provide, movie recommendations to people or something, it really doesn't matter if that's terribly consistent or not. You would always favor availability over that. And that's why a system like Cassandra might be a better choice for that sort of a system. But if you're dealing with financial transactions or something like that, consistency is all that matters, and you're going to have to deal with the complexity of something like ZooKeeper. So anyway, that's how ZooKeeper works. Let's go and play around with it a little bit, show you that it's a real thing. It's not going to be a terribly interesting exercise, because all we can do is really connect to ZooKeeper and write some stuff and see that it actually does something. But why not? Let's go get our hands dirty with ZooKeeper. See what I did there? We have a picture of a ZooKeeper with an elephant, the Hadoop symbol. I'm so clever. All right, let's go fiddle around with it, shall we?